You will find a link to this poll in the description. Please take a minute and fill it up. Hi, I'm Shaul. In this video I would like to address some issues related to the phenomenon we call 3D pop. Those issues will include some biological, some engineering and some semantic aspects of this phenomenon. First of all, to understand exactly what it is and how it is created, we must remember that our eyes are not perfect optical instruments. They do disperse light, and they disperse light quite heavily. So once the image passes through the eye, gets to the retina, it already has quite a lot of chromatic aberration. How much chromatic aberration? Well, the physical or mathematical representation of the propensity of transparent material to disperse light is the Aber number. And the Aber number of the eye is 45 on a scale that goes between 0 and 100, where 100 is a complete resistance to chromatic aberration. Typical glass types have Aber numbers between around 35 and 65 or 70. ED glass or low dispersion glass has a typical Aber number of 80 to close to 100, about 95 or 98. So to create an image that is similar to what we are used to see with our naked eyes, there must be quite a lot of chromatic aberration, i.e. a low Aber number. So lenses that create a true-to-life image should include a lot of high refractive index glass or flint glass, which has a lower Aber number that allow more dispersion than other types of glass, crown glass or ED glass. The most evident symptom of chromatic aberration is fringing, color fringing around the edges, where typically surfaces that are in front of the focal plane display green fringing, and surfaces behind the focal plane display blue or purplish fringing. But chromatic aberration does not only affect edges. This is what we can see when we pixel peep. Chromatic aberration affects the whole image. And in particular, it affects the appearance of the curvature of surfaces, which is an important cue for our brains to perceive the shape, the volume, the weight of objects that are photographed. To my eyes, there is a clear effect of dispersion on the gradations we see in the two-dimensional photograph. The more chromatic aberration, the more there is a mixture between adjacent surfaces and the more curved surfaces appear. Microcontrast is a term that has been used to describe this visual effect. But I think that the better term to describe it is microgradation, because this is what it really is. Microcontrast is better related to edge sharpness. I recently suggested a function or a formula to predict the rendering of an optical device or a photographic lens. I call this the dispersion score. It is calculated by subtracting the number or the count of ED elements in the lens from the count of complex groups. A complex group is a group that is made of more than one element. It can be a doublet, which is made of two glass elements cemented together, or a triplet that is made of three glass elements. The result of this subtraction is then divided into the total count of elements in the lens. The higher this dispersion score, the more true to life the rendering will be. The use of complex groups in this formula is a simplification. What is really interesting is the number of high refractive index groups that imitate the lens in front of our eyes. But most manufacturers do not give us this information. It can be assumed that in each complex group there is at least one high refractive index element. So to make the ground level between different lenses, I would use the number of complex groups in the formula even when the number of high refractive index elements is stated. In this way we can compare different lenses without any bias. Besides, in most cases, the number of high refractive index elements is very similar to the number of complex groups. There are some outliers to this formula. For example, lenses made by Cosina that are branded as Zeiss or Falkland. These lenses use a special type of glass that is referred to as atypical partial dispersion or anomalous dispersion glass. This glass refracts light in a differential way. For short wavelengths, it acts as a high refractive index glass. So it does refract the blue side of the visible spectrum. But for green and red wavelengths, it acts as a low dispersion glass. Lenses such as the Zeiss Batis 25 millimeter f2 or the Falkland 21 millimeter f1.4 or the new 28 millimeter f1.5 have quite a bit of chromatic aberration, although they contain a few elements made of this partial dispersion glass. So I would make this glass a special case in my prediction formula and treat each such element as half power, which means I would multiply the number of ED elements by a factor of 0.5 to get a more realistic estimation of the effect of this glass on the rendering of the lens. In the case of German branded lenses, I would pay special attention to the apochromatic or apo designation. In these lenses, more attention has been given to suppressing dispersion, and I would treat those lenses as basically flat rendering ones. More generally, I would pay attention to some reviewers who focus on the technical aspects. People like Dustin Abbott or Gerald Andan, who really scrutinize the properties of lenses in very detailed manners, are important assets to me because unknowingly they can really give me a good idea of how lifelike the rendering of a lens is going to be. However, instead of dismissing optics that display a lot of fringing along edges, I tend to like those lenses and I see them as good candidates for the photography I like to do. Looking at the response curve of the ratio of the population perceiving this dimensionality effect, looking at the response curve of dimensionality perception versus the dispersion score, the difference between dispersion scores higher than about 0.17 is quite flat. So I would say that 0.17 is already enough for a lens to display good poppiness or dimensionality. However, lower values do play a significant role in the perception of the rendering. Something else we can learn from this response curve is that only about maybe 80 to 85% of the population would see this effect or differences in rendition. In other words, up to 20% of the population uh, cannot see differences in rendition at all. And that brings us to the final point of discussion today. The semantics or the terminology best used to describe this effect. The vernacular term to describe it is 3D pop, but it is not a very well defined term because pop can refer to dimensionality, it can refer to differences in sharpness that are an effect of depth of field, where the subject is much sharper than the background. It stands out. And it can also refer to differences or contrast in color. Given that some of the viewers would never see the effects of dimensionality, it becomes quite confusing. Other terms that could be used are dimensionality, as proposed by Camera Mystique, or immersive dimensionality, as suggested by a viewer of this channel named Gary. Now, personally, I feel that dimensionality is more of an engineering term, and it is not very well understood. What I like to use is terms like true-to-life rendering or lifelike rendering. But those terms are related to the content of the image. It can be argued that photographs with human subjects or natural, organic subjects would automatically become lifelike. Another term I just thought of would be I-like, which emphasizes the neurobiological aspect of this rendering, where the lens emulates the optical properties of our eyes. I have put up a poll in which I would ask you to stress your own opinion on the best terminology to describe this phenomenon, or possibly suggest a term of your own that would best describe it in the most comprehensive, understood manner. You will find a link to this poll in the description. Please take a minute and fill it up. It is important that when we mention the poppiness of lenses, we talk about the same phenomenon or the same thing. Right, that will be all for today. If you want to support this channel, please buy me a coffee. It's a nice gesture between gentlemen. You will find a link in the description. So thank you for watching, and see you again soon.